achieve a signer, let's say from 20, if your signal level is just NEC 110 dBm. So that was for the downlink. Now if we look for the uplink, we will see the following. So of course, the farther away you are from the base station, the more power the UE needs to transmit back to the base station. So therefore you have this trend. So what we can see here on the left-hand side and the right-hand side, we have two different LTE devices. So, and here you can see also that the used TX power is different. So everything depends a little bit on the implementation, which is done by the supplier of these devices. The green line is exactly the same in both graphs, so you can see the differences here. But now let's entering the next level, which is definitely 5G. So first of all, let's have a look at an isolated 5G site with 3 sectors, and each sector has 3 beams. So first of all, we can see these are measurements taken from a network scanner, that we have a brilliant separation of these physical cell IDs, or physical cell identifiers, or as we say, PCIs in short. So where you can see the areas of green, blue and red ones. Of course, there are some reflections just circled here, which are natural, and these are the challenges you know already from the LTE network. So the mobile network world is not perfect. So these are the challenges the optimization team have to fight with. Now in the next level, we will have a look at the individual beams per cell. So I was talking about that we have 7 beams per cell, and you can see here, just indicated by the lines, the 7 sectors are really sharp, so that you can differentiate these. Now let's have a look at the correlation plot signer versus RSRP measured by the network scanner. So the behavior looks very similar to that what we are known for LTE networks. So we have again the same behavior, the same line, which is just to guide the eye, so where we see the theoretical limitation of the signer independence of the RSRP signal level. There is a small gap highlighted here in red. So this is due to a signer degradation, but this has not been further investigated in this measurement. Of course, you want to see where are the outliers are coming from. So most likely we were thinking about it's coming from overlapping cells or causing interference. So therefore, in this presentation on the right-hand side, we colored the number of cells which are measured by the network scanner in different colors. So what we call top-end pool. So a top-end pool actually describes how many cells can be measured within the dynamic range of 20 dB of the scanner. So that means if the best cell has, for example, a value of NEC 80 dBm, all cells which are within NEC 80 dB to NEC 100 dB can be measured and are simply counted. But as you can see here, that the signer degradation is not necessarily coming from overlapping of the cells and must have other reasons. Now let's compare the scanner measurements with the mobile measurements. So in this graph, I show you the scanner measurements from the previous slide, the blue bubbles, together with the measurements from the mobile, the orange bubbles. So here you can see that the maximum signer depends on the implementation of the device. For the scanner, the signer is kept at 30 dB, and for the device, in this case the Samsung S10, the European model, has a limitation of 25. So this is simply dependent on the implementation of the mobile manufacturers, and we have the same in LTE already. So the very good correlation can be seen here between the network scanner and the mobile network, which is very good. Of course, there's one very important thing I want to highlight, and this is that the network scanner is much more sensitive compared to the UE. Where the UE can measure only down to signal levels of NEC 125 dBm and a signer of NEC 5, the scanner is more sensitive and can go down to NEC 140 dBm and NEC 15 dB for signer easily. So, but what about the LTE performance? of 5G devices today. So if we do the same investigation, SINA versus RSRP, but now measured for the LTE network, we see this behavior. So the same behavior as we know from the first days of LTE, the same curves added here just to guide the eye. And what you can see further is that the blue bubbles, which are corresponding to band 20, are really, I would say, looks like a cloud. So because the LTE 800 network is heavily loaded, and this causes a massive SINA degradation. If we compare the SINA versus RSRP from this 5G device for LTE and 5G measurements, we see exactly the same behavior, so a very good correlation. If you are interested in to understand where some outliers are coming from, you can do a further drill down by filtering to the specific PCIs as shown on the next slide. So the area with the unexpected results is circled here, and you can see clearly that all these unexpected data points are belonging to the green PCI. Furthermore, we can see that for the blue PCI, we have a much better SINA value compared to the other twos. Additionally, we can do a drill down also to the specific SSB indices per cell. And the SSB indices are colored also in the three graphs. Also again for the same PCIs from the previous slide. If you have a closer look, you can see that the SSB index 3 and 4 is mainly responsible for the occurrence of the outliers. Looking at the TX power versus RSRP for LTE and 5G devices, so first of all the LTE behavior I showed previously, and now comparing with the TX power versus SINA from a 5G device, more or less the behavior is the same. So for LTE we saw that the maximum TX power is achieved for signal levels below NAC 85 dBm. In contrast to that, the maximum TX power is more or less used instantly for the 5G devices. Also interesting to see that we have two discrete branches of max TX power. I have to emphasize that these are measurements from the first 5G commercial available devices, and we saw much better results from upcoming devices, which I cannot show today due to NDA reasons. Now let's have a look at TX power versus RSRP for LTE and 5G. So on the left-hand side, we can see the measurements coming from the 5G device for LTE and 5G, and on the right-hand side, the LTE results from the 5G device compared with the results from a 4G device. The overall shape of the curves are more or less the same, so that means that the behavior in LTE and 5G is similar. All the measurements I showed so far were for frequency range 1. Now let's have a closer look for some results coming from the millimeter wave frequency range 2. In this graph we see coverage measurements in an area of 0.8 square kilometers covered by 21 G-node bees. The majority of measurement points are below NAC 120 dBm, which is a very low signal level and cannot be measured by any 5G device, or you will not get any good service here. So what we did, of course, here we did the measurements with the scanner. So the scanner is, as I said, much more sensitive like a UE, and in the next step, filtering out signal levels below NAC 120 reveals many blind spots, which are actually showing the mobile view. So the 5G network looks really fragmented, and talking back to the customer, it turns out that only 5 G-node beats from 21 were operating and transmitting. So this is a clear proof that measurements with mobile network scanners can help you to identify deployment problems. So please let me conclude what I showed you coming from the test results. First of all, the 5G behaves more or less like LTE with the same optimization challenges we already know from LTE. So there is a good correlation between network scanners and mobile measurements. Both devices are needed for optimization tasks. The scanner, of course, is much more sensitive compared to a UE. Interference will be crucial to investigate also in 5G networks, the same as we know for LTE networks. Siner versus RSRP is a very powerful correlation plot to investigate interference issues in the network. Further drill down to specific PCIs or specific beams can help you to understand where the outliers are coming from. First 5G devices are showing poor RF performance, especially in the uplink, but as I said, we saw already much better performance for upcoming devices. That means keep your eyes critically on smartphone RF performance. This was a short insight into the first measurements we achieved in 5G commercial networks. I would like to hand back to Arndt to bring you to the latest achievements we've got with applications.
Thank you, Michael. Very nice insights into 5G early deployments, networks, as well as devices. We promised at the beginning a forward look into the emergence of new, more interactive and real-time use cases supported by 5G. Let's do that. Who uses 5G in future and how? We have new classes of users in 5G. Humans, of course, humans are not really new, yeah? But we will still have smartphone use case here in 5G as well. But new use cases are in 5G and in the upper part of the 5G triangle, enhanced mobile broadband. The trend is towards more interactive applications and use cases, and that's a clear trend we have to follow. New use cases are clearly, and new user classes are coming from the automotive segment, autonomous driving, vehicle-to-X communication, and Industry 4.0, smart warehousing, smart manufacturing, and this is, here we see as well private 5G networks that make sure that you have network connection within factories. And for really low latencies, we need really standalone 5G. All deployments today are 5G non-standalone, and that means we have always the LTE anchor, where in the LTE core network, and the just 5G as a data layer in combination to the LTE anchor. And for low latency, the LTE packet core is the clear limitation in terms of bringing down the latencies. I think we can ignore the IoT and massive machine type communication cases as well here in 5G, because 3GPP is not really specifying anything specifically here for this corner, left lower corner in this 5G triangle. Everything is done by narrowband IoT and LTE-M. And each of these user classes generates an individual traffic pattern. Yeah? And we have individual requirements towards the network. And an optimized network of human users may not really deliver the good performance for cars and industry for really high, reliable and low latency communication cases. What are these more interactive, enhanced mobile broadband applications? And here we see e-gaming and augmented reality, virtual reality. What is the combination between service, application and use case? The underlying service is always UDP or QUIC. QUIC adds a certain forward error correction to the UDP connection here. It gives a certain security for this connectivity. The application is AR, VR, augmented reality and virtual reality. And we have different use cases using the same application, AR, VR, but they are completely different. For example, if you look to this augmented personal trainer, it doesn't really care if the personal trainer is shouting at me, is motivating me 100 milliseconds or 200 milliseconds later. Yeah? Or retail shopping, AR, VR, retail shopping. If I would like to see me in a new suit, it doesn't matter whether the signal I see me 100 milliseconds or 200 milliseconds later. Yeah? But if we go to this assisted surgery, the clear demanding requirement where the doctor and the surgery robot are 1,000 kilometers away from each other, it makes really a difference. And here it's very clear that there need to be very low latencies, very short reaction times, yeah, so that the robot is really stopping cutting with a knife when the doctor wants to. So individual QoE models are needed here for individual use cases. I think it's clear that we never can implement all different use cases in our test systems having all tailored QoE requirements. So there need to be something new. We need new ideas here. So what does the standard require? 3GPP, here you see the system architecture of 5G systems. one of the latest drafts of release 16, and you see there's a table with 5G quality indicator, 5QI here, and you see number 3 is real-time gaming, and you see a packet delay budget, 50 millisecond, and a packet error rate, 0.1%. So that is for real-time gaming. If you scroll further down on the table, you see as well here low latency, enhanced mobile broadband applications, and augmented reality. And here you see a packet delay budget of 10 milliseconds, very strict, and a packet error rate to the 10 to the power of -6. So that is really, really tough requirements. And this, I think, is made as well for this very demanding case for remote surgery. So testing interactivity, that opens the door into the future 5G use cases. So as said before, the future will be more interactive, more real-time. And there will be these new interactive applications. But what does it mean, interactivity? Yeah? For us, interactivity is a combination of bitrate, latency, and continuity. Yeah? So we need certain data transmitted with a short latency and continuously in a certain packet stream. That is interactivity. Latency, transport response time, of course, continuity, that shows interruptions or undercuts of required data rates. Of course, packet error rate, packet loss will be seen here as well in the continuity. 3 dimensions, we like triangles, that's always nice. And you can basically fill in all different use cases here in this triangle. Very simple, a data download only requires bitrate. No demand on latency, no demand on continuity. A 4K video stream, that's a real-time stream, requires high data rates, of course, because we have high-resolution videos. Nearly no requirements on latency, because normally you have 1 or 2 seconds buffer time. And a certain requirements on continuity, because you need a certain continuous data stream. And then ultimately, in blue here, you see augmented reality, and that is this extreme case where you have very high data rate, you need very strict requirements on latency, very short latency here, and a very high continuity, a very high packet rate. And this altogether, bitrate, latency, continuity, that forms interactivity for us. And this we want to test. How we test that? So we are proposing a new interactivity test, and we implemented that already. So, and the process is that there is a device, a smartphone, that sends UDP or a quick stream of unique packets to an active server that immediately reflects this data. And there are packet rates, they are certainly configurable between 100 to 1,500 packets per second, and that forms for us a certain continuous data stream. What are the control parameters for us? First is packet rate, can be high, can be low, and that is driving the continuity. We have the packet size, can be small and large, and the combination of the packet size and the packet rate, that is the bit rate that we need for transmitting. Third point is the delay budget, and that forms for us the latency requirement. And any packet that is above the exceeded delay budget, then of course we have to count that as packet loss. So the results of our test will be a bitrate in transmit and receive direction, uplink, downlink, a round-trip latency plus a packet delay variation, which is the latency jitter, and the third is the packet error rate, because we know what packet is not reflected, what packet is lost. What is the technique behind? If you hear latency, everybody's thinking about ping, a ping test. We are using here the T1 protocol, that is the two-way active measurement protocol, and that is specified by IETF. So there's a certain RFC here, standard document. Why we use that and not ping? Because ping is not really made for measuring times, measuring round-trip times. Of course, you get, if you start a ping test to a certain server, you get a time back, which is the ping time back. But the task of the ping test is just to see whether the server is accessible. Yeah? It's not how quick the reaction is. So in particular, if you go for very low latency measurements, ping is not the right way to do. So we are using T1 protocol, and then the basis for this is it's really made for measuring times, measuring round-trip times. And it's also good for verification of service level agreements, very important, and therefore we are using this protocol. We implemented that already in our QualiPoc Android software in Android Native to really minimize the influence of the operating system. Of course, we need a certain server installation somewhere. We can say that many internet nodes like firewalls, routers, other infrastructure, they support T1 already now. We will also deploy an own server installation for that, and we also offer service packages here for private installation of these kinds of server installations supporting the T1 protocol. Okay, how will the new interactivity test look in practice? So we have a predefined traffic pattern, and we try to emulate certain applications here, and we are focusing here today on e-gaming. And we are looking to e-games in highly complex multiplayer scenarios. That is very important here. Constant packet flow is key here, can be low, can be medium, can be high, but we want to see here really a constant packet flow to really check the continuity. Yeah, e-gaming. We found out that in most of these cloud-based e-games, network e-games, in complex multiplayer scenarios, they work similar with a certain traffic pattern, and there's a 10-second phase of activity for a certain action. Yeah? And that's an initial phase at the beginning, a highly interactive phase, and here you see bit rates up to 1 megabit per second here, and then you have a sustainable phase and a trailing phase at the end, and that concludes the traffic pattern for one e-gaming action of these complex multiplayer scenarios in e-games. And the measurements that we take are achieve bit rate. Of course, we try to see whether we can match really this traffic pattern. Packet error rate, is there any loss that we see? And of course, round-trip latency and packet delay variation for each phase and for the overall duration. And all these together will form the interactivity score for e-games. And of course, we need a certain score for that. So we need a QE model that provides a certain interactivity score that rates the network, that scores the network, how it's applicable, how it's prepared for e-games. So, and doing this, emulating these real applications, we basically can then apply a certain qualitative experience model. And the model will provide us more or less a synthetic MOS mean opinion score, and that is based on quality of service and on technical KPIs. And the technical KPIs are latency, round-trip time, as we said before, and this is one part of the equation. Latency over time, and you see here the graph, that is these famous S-curves, where you see the interactivity score from 0 to 100%, and you see the x-axis here, the round-trip time, or the round-trip latency, as we call it. But there are more components, more factors into this equation here. The second factor, F2 here, is delay variation. That's a factor basically between 0 and 1. And another factor that is driven by the packet loss, also from 0 to 1. And that means we have the curve is coming from, the interactivity score is coming from the latency, and the delay variation and the packet loss, they will scale down this curve just on the y-axis here, scaling down the curve coming from the latency. That's basically the equations here. And I would like to promote here also one of our white papers on our website describing this interactivity score. Good. What are results in practice? Of course, we want to see how this interactivity test fits into the game. Is it really providing good values, good scoring for networks, different networks, for e-games, for cloud-based games? Okay, let's look into this. And here's an example for 5G. ENDC, so that's non-standalone, it's always an LTE anchor, and we have the LTE packet core, very important. And here you see the interactivity score driven by round-trip latency, you see 36 milliseconds, packet delay variation around 14 milliseconds, and a packet error rate of 0, so no packet was lost. And then, of course, in our smart analytics tools, you will be able to see finally for this one 10-second long activity in the e-game, you will see the data rate, that is the light green curve here. Remember the traffic pattern. And you see, of course, the curves for the round-trip latency, also low values, 10th percentile of round-trip latency, and other values as well. And you see the interactivity score. In this case, it was 82%. We can say that everything that is better than 70% is really a good score for e-games in this sense here. Remember, 50 milliseconds is the requirement coming from the standard. Another result here, another 5G test here, round-trip latency is really good. You see now it's below 30 milliseconds, so 29 something. Packet elaboration, 40 milliseconds, no packet error rate here, no loss. And you see an interactivity score of 87, more than 87%. So that's a very, very good interactivity score here. Some details to this measurement, and you see here, first of all, the throughput, in this case here in uplink direction, and you see the median round-trip latency, and you see all the green dots here are round-trip latency measurements per packet. That means for every packet, we provide a certain latency figure. We have all these things in the details, in the detail of the database. And of course, we want to provide the median value here as the result for this 10-second period. Very good round-trip times here, a very good latency, and very good interactivity score. Now let's look to a 4G network, LTE network, and we can say that was a very well-developed, well-optimized network. You see here round-trip times around 39 milliseconds, a little bit below 40 milliseconds. Packet delay variation 60 milliseconds, so really good values. And the score is also really good for this LTE network, 79%. Why we don't see a real difference here between the 5G and the LTE? Clearly, the limit for the low latency is basically the LTE packet core, and that we have still in the 5G non-standalone case. Yeah? So really, the 5G enhanced packet core is limiting to bring down the latency for the 5G example here. Also, the details for the LTE case. Round-trip latency is okay to good, I would say. And also, it's now all the packet-based latency figures are around these 40 milliseconds here. And it provides a very good interactivity score of nearly 80%. How does it look in 3G and wideband CDMA? And you might think, hey, we are talking about 5G here. We are talking about an interactivity test, and this is agnostic of the technology. That means it can be adapted to 5G, to LTE, even to 3G networks. And that's what we did here. Now we checked the interactivity score for e-games in a 3G network. And you see, round-trip latency, 50 milliseconds, not so bad, and very good packet delay variation, latency jitter around 10 milliseconds. But you see here a packet error rate of more than 3%, which is much too high. Required is 0.1%, 3% much too high here. And this brings down the interactivity score to 60% roughly. Let's look into the details, and here we clearly see, okay, in particular in this interactivity time where we need 1 megabit per second, instantaneously here, you see that exactly in this point, the wideband CDMA network seems to be congested. And that means we lost packets here, in particular in this interactivity phase. So the latency round trip is quite okay, but we have packet error rates higher than expected, and therefore this higher packet error rate, that decreased our interactivity score. Okay, that were a few examples now, and now we have to think about what we do with that. And what we need is a scalable concept, and that's very important. So let's look into the next slide here, and basically we see the interactivity score for e-gaming, and what we can do now is to play around with the parameters. And we say it's fully scalable. On the upper right side, you see now an interactivity score for low activity e-game. Yeah? That means the requirement is relaxed. Yeah? So we accept now more delay here, for a certain score. On the picture below, you see an interactivity score for drone control. If you want to control a drone via 5G, of course you need fast reaction times, you need lower latencies. Why not taking this model and just increase the requirements? So make it tougher, make the required times tougher. And that's what we did here on this slide. And this is basically finally coming up to the conclusion that our interactivity test can really be adapted to other use cases that also require tougher latency requirements. And here we can say, why not taking the outlook into URLLC of 5G industry applications? This model, this QE model, might be fitting, might be matching the requirements we need for robot control, for interactions in smart manufacturing, for example, requiring very low latencies. And based on this common set of technical parameters, you see on the bottom the technical layer, RF IP application, we base then our KPIs and our quality of experience on, and we can scale basically different QE models based on these technical layers below. So we could realize different QE models for different interactivity use cases. And that is the scalability we want to provide. Okay, now we should talk a little bit about the test solutions to generate all these results. First, on the left side, you see field service installation and spectrum clearance. Be aware, you recommend it to clear your spectrum clearance before you launch the network. Your site acceptance on the lower end, of course, base cases need to be accepted whenever you deploy correct infrastructure deployment. The middle part, all the passive measurements and active measurements using scanners and smartphones with the QualiPOC Android software, that is exactly what Michael explained in the network test results in the middle of this webinar. ROMUS, of course, as well as real-time analytics tool. Verified network quality during operation. And on the post-processing side, for the data analytics, we have our Smart Analytics software solution, and that is basically providing the screenshots that you saw before. QualiPOC, in combination with Smart Analytics, that will provide finally the interactivity score as well, as we talked in the webinar. Keywords here, quality benchmarking and network monitoring. And if you want to know more about our products, please visit our website. You'll find all the different details there. Okay, we come to the end. Let's talk about the conclusion a little bit. First, commercial rollouts in 5G are running now, and you saw in our information here and in websites of operators, rollout status is varying really significantly these days. Our network measurement tools that we provide, 5G network measurement tools, are really helping for rolling out networks, validating, optimizing, and troubleshooting 5G networks. The RF performance improvements that we could really see now in the upcoming new smartphones. An interactivity test that is combining round-trip latency, packet delay variation, and packet error rate. Finally, of course, the proofing bit rate. And we combine all in one single test. And this interactivity is key for future applications. An interactivity test that we recently released here with Roland Schwarz allows for these scalable QE models. And I think we can say we are 5G URLLC ready, in particular, even as well for low latency communication cases in smart manufacturing, for example. We as Roland Schwarz Mobile Network Testing provide a complete portfolio of 5G network test solutions to maximize network quality and performance. And maximizing network quality and performance is our mission. This is the end of our webinar. We hope you enjoyed this insight into the reality of 5G today. We look forward to future discussions.
And finally, don't forget, keep on testing. Thanks for watching and stay tuned.